Okay, now, this chapter is all about work and energy both. And the reason why they're about both is because they're technically the same thing. They're both measured in joules. Definition of work is the result of creating energy. Energy is created from work. They're related to each other. Both have joules, like I said. The word kinetic comes from the Greek word for motion, kinesis. Many college universities have PE majors classes. Kinesiology, a friend of mine took it, had to describe a forehand topspin shot on a 5-page paper. Rather impressive. I read it. It was really good. And like I said, they're considered to be the same thing because they are measured in joules along with work. The simple formula for it is K, which is kinetic energy, equals 1/2 mv squared. Now, I could sit here and tell you to memorize that, and it's something that's really easy to memorize, but you know me, I don't like just giving you a formula and say, here, learn it. If I can avoid it, sometimes you can't avoid it. But in this case, I'm going to show you how this is derived. Now, you don't have to memorize this, but as I said before, you're going to have professors who do this all the time, particularly in calculus, but also in physics, where they derive stuff all the time. And especially physics with a calculus bent. For those of you going into engineering, you're going to be taking calculus or physics with a calculus intention behind it. So, we'll start off with the definition of acceleration, which, as you know from your toolbox, is the change of velocity with time. And change of velocity means Vf minus Vi over that t for time. In an accelerating object, the distance can be calculated by taking the average velocity times time. The average velocity is the sum of the two velocities divided by 2 times that time. So what we're going to do is we're going to take these two and multiply them together. So this goes here, and this goes here. And as you see, there's a t in the numerator here, and a t in the denominator here. So they cancel out. Then you're going to multiply this, and this is a difference of squares. So this is going to be Vf squared minus Vi squared over that denominator of 2. Now, the next thing I want to do is get rid of that d, the acceleration by itself, because that's going to be important in what I'm trying to do. So I divide by d, and I get the d in the denominator here, otherwise it's the same thing. Now, the definition of force is mass times acceleration. So, I'm going to multiply mass times this quantity right here for acceleration, and I get this thing. Since work is defined as force times distance, then I'm going to take this whole thing right here and multiply it by d. Well, because I have a d in the numerator and d in the denominator, we're going to cancel out. And this is what I have left over. Mass times v squared minus vi squared over 2. That is my work. And this is by definition delta v squared. Okay? So, I just changed that. I moved the m up here with that for reasons that's pretty clear from how I started this. And as I said, work and energy are the same thing, so this is the expression for work, is the expression for energy. And if it's energy, it doesn't make any difference what kind of form the energy is. Energy is energy. We're going to look at it from the point of view of kinetic energy. Now, why are we looking at it from the point of view of kinetic energy? Because velocity means it's moving, and the Greek word for moving is kinetic. And so at rest, starting rest, that means then that the delta V becomes just V, or V final, because VI is 0, so that gives you 1/2 mv squared. Now, if it's not starting at 0, that is possible, then instead we don't say it's K, we say it's a change of K, and it's going to be 1/2 times the mass times the change in velocity quantity squared. So that's the derivation. We generally use this one right here because most of the time, in the problems that we're going to be dealing with, we're going to be dealing with an initial velocity of 0. So, it's probably not a bad idea just to try to do that derivation on your own. Just so you learn the habit of what you're about to experience next year. All right, so let's take a look at the example. So what is kinetic energy of a 20 kilogram bike that is going 20 kilometers per hour? In order to have joules, you must change the velocity to meters per second. So if you do that, and this is the conversion right here, we get 5.56 meters per second. So K is 1/2 times the mass, 20 kilograms, times the change, or times velocity, is 5.56 meters per second squared, and we get 55.6 joules. It is that simple. Your practice problems, page 176, problems 29 through 32. Good luck.